Crippa. I'm a senior research specialist at the Department of Medical Epidemiology and Biostatistics at Karolinska Institutet in Stockholm, Sweden. Today I'm gonna give you a talk about meta-analysis of dose response studies with the dosresmeta R package that I wrote, and this is gonna be the outline for the talk today. I'm gonna present this as a vignette of the dosresmeta package. I will cover the very basic idea or rationale behind the dose response meta-analysis. I will talk a little bit about the aggregated dose response data with a practical example, and then I will cover the two different phases of the analysis. So the dose response analysis for a single study, and then how to perform this same analysis when we have multiple studies. I will cover the main feature of the dosresmeta package as originally thought in the first implementation, and I will also talk about some of the model extensions that have been recently implemented, and I will conclude with some references and codes. So what is dose response meta-analysis? Dose response meta-analysis is a technique, an analysis, where we want to derive a dose response curve from results that have been published on different journals or on different resources. And these results try to summarize the association between a quantitative exposure. So we're talking about, for example, number of cigarettes. We are going to see how we are going to use a number of cups of coffee per day, and then we want to relate this exposure to the occurrence of a health outcome or some other outcome. We will focus on mortality risk, or some other example could be incidence of a disease. So the research question that we can address with this methodology is to evaluate if there is an association between the exposure and the outcome, and what is in particular the shape of this exposure. And in such a way we can define also which are, or try to identify those exposure intervals or doses which are associated with a best or worst prognosis on the outcome. And then we can also try to identify those factors that may explain differences in the association. We're going to see some example later on. But just to give you a little bit the idea of the importance of this technique, it has very different field of application. Many dose response meta-analyses are currently published in leading medical and epidemiological journal, and they are also used frequently by international health organization and academic institution. So many of the measures that are currently reported by public health agencies are actually based on this meta-analysis. Let's have a look on the aggregated data. They are the basis of this meta-analysis, and we're going to do this by using as a motivating example one of the dose response meta-analysis that have been published in the last years, and this is about modeling the association between the coffee consumption and different health outcomes, in particular all-cause mortality, cardiovascular mortality, and then cancer mortality. We're gonna use all-cause mortalities in this example. So I'm gonna put some of the code so you can also reproduce the results in the slides. We're gonna see, for example, how this by loading the dosresmeta R package, the data are included in the coffee mortality object, and you see a little bit the structure of the data. So we have two different studies that they report as a measure of association, the log relative risk with the corresponding standard error for different doses of coffee consumption, and they use the first doses as a referent, and they then compare increasing doses, how the log relative risk changes for increasing doses of coffee compared to the referent one. Let's see how we can run a dose response analysis based just on one study. And we're going to I'm just going to present some descriptives of the studies. So here we see the study by Legrady in 1987, and we see how using half a cup coffee per day as a referent, we see a slow decrease in the risk or in the mortality risk for increased doses, and this reduction then disappear and higher doses. So the key feature here is that all these points are not independent because they are based as a relative comparison using the first group as a referent, and then because of this the relative risk in the relevant group is equal to 0 or to 1, or the log of this one number equal to 0 by definition. So what we're going to do is we're going to run a linear model, actually a log linear model, where we have as outcome the log relative risk on the non-referent doses, and then we have a design matrix where it's going to specify how we're going to model our relationship. And again, the model is without an intercept because by definition the relative risk is equal to 1 on the referent dose, and then we can estimate or approximate the covariance of the residuals using additional information. So depending on the study design, then we can use the information about the number of cases or controls, or for core studies about the number of participants and the person times accumulated to estimate this covariance. And here we can use the covar log RR function to exactly do this if we are interested in having a look at that quantity. And then here I'm going to show how to run a linear trend again for one single studies, and then how to use the ci.exp function in the AP package to interpret the results. In this case, we will interpret that every 1 cups increase in coffee is associated with a 3% increase in the mortality risk. Of course, we've been seeing that from the actual data this might not be appropriate, so we can run also a nonlinear model, and here I'm using restricted QB spline in the RMS package. And now the output is a little bit more difficult to interpret, as the coefficient they don't have a strict interpretation. So we can see that there is an evidence of an association. So this is a p-value tested that both of the coefficients are equal to 0. And then here we see that there is also evidence of a nonlinear relationship as dictated by this p-value. So how to interpret the results? Then we can predict those in terms of predictive relative risk, and now we see that there is a better agreement with what we'd expect. Now, having said this, so we were able to estimate the dose-response association based on published results from one studies. What happened when we have multiple studies? So basically, I'm expanding what I did before to just display the data that we want to model now. And by applying the same 2 models to all the studies, then we are able to also get the same prediction for all the studies. I'm not focusing on the code here, but you can copy and paste to reproduce it. And then you can see that there is some variation in the observed results, but a tendency in an inverse association, which might not be linear in most of the studies. So how can we summarize this evidence? Then we are doing a meta-analysis. So basically we are taking all the coefficients which specify the dose response association, so the beta coefficient that you were seeing in the output before, and then we are running meta-analysis to combine those coefficients. Here I'm just reporting formulas for the univariate case, the linear trend, but then we can expand those also in the multivariate setting using multivariate meta-analysis. So in general, we have tau squared, that is the between study heterogeneity. Then we can test if there is evidence of overall association, and then we also can quantify, test the heterogeneity, or quantify the impact of this using different measures. And here just showing how you can do this using the Meta-4 package, or in the case of the linear setting, or using the other packages. Here I'm using the MV Meta by Gasparini for pooling multivariate beta coefficient. So having said that, I will cover instead how you can use and why I implemented and released the dosresmeta package. So the dosresmeta package facilitates the two different analyses, so both the dose response analysis and the pooling analysis, so you don't have to implement yourself or using different packages, and so in such a way you get a most comprehensive framework for the two analysis altogether. And then of course there are additional functions to ease different tasks of the meta-analysis, such as testing, predicting, and interpreting, and meaning that presenting also the results. And then I also implement a set of extension to the basic methodology. So I'll just show you how to do in 2 lines what I did before in several steps. So now with the function dosresmeta, if I specify the ID arguments, specifying different studies, then I'm able to estimate an overall linear trend. And again, if you want to interpret, you can put on you can exponentiate the coefficient and then interpret as an overall 3% decrease in mortality risk. If we are not satisfied with a linear model, then we can turn to the non-linear model. Different options are available. I also have some code for fractional polynomials, other non-linear model like a log exposure model. Here I'm using again for comparability as with the previous example, the restricted QB spline. And again, here you can test if there is an overall association. You can look in the Q test, and here you're going to have evidence of a significant residual heterogeneity, and then you can quantify the impact of this heterogeneity to be around 60%. How to present the results? We can use the predict function implemented for predicting on a new data here that is specified, and just putting a 0 at the beginning. So this is going to be my referent, and the values are presented on an exponential scale since this is our unit of interpretation. And then we can see that there is an overall non-linear association with the lowest or highest decrease in mortality risk between 3 and 4 caps per day, as discussed in the paper. So from this we can do more, of course. We can try to predict the results of a future study, or try to predict the results on the individual studies using the BLUP, the best linear unbiased estimated prediction. And so in such a way we use the normality assumption on the random effects to get a better prediction of the individual curves. And I left here the formulas for the linear, so the univariate case, but then I also presented some of the slightly more complicated code to get the actual curves. And you see that here as a dotted line I'm presented the BLUP, so the and I compare to the individual curves that I was presenting before, and you see that somehow these curves are more close to the average than the individual curves, using some of the information that we've been gaining from the model. Just briefly sketching some of the additional capabilities. Here we've been discussing, implementing, and publishing how to evaluate the goodness of fit using different measures, the deviance test, the R-square as a coefficient of determination, or using a plot as of the decorrelated residual to better evaluate the agreement of the model. You see here we're using the function GOF, how to get this quantity and how to get a plot investigating the potential influence of some of the points. And of course there are more to do in the meta-analysis. Here I'm just presenting the meta-regression or stratified analysis to try to explain some of the residual heterogeneity in the model, and this has of course some advantages because it gets more knowledge or new results, but of course it gets a little bit complicated by the limited number of data points, and this is by the limited number of studies. It's not those data points that make a difference. So I can show you here how we want to explain the residual heterogeneity using the extra argument mod as a function of the geographical area, and then we can of course use the wall test function to test this hypothesis, and we see that there might some indication of differences of those response association between different geographical area. And again, if we want to present this data, we see that the American, they have a lower mortality reduction as compared, for example, to Europe, and then we see a really strange curve for Japan. If we look more into this, we see that this is actually explained by a very narrower exposure range, so limiting to up to 3 or 4 caps per day as a maximum observed range in that studies. And just to conclude, I will just sketch a few model extension. One I was covering, it was the one-stage procedure. So this is a more comprehensive model strategies, is equivalent to the two-stage procedure when we have the same available data. But of course, the one stage is a more general framework, is conceptually easier, can fit more elaborate curves, and avoid the exclusion of studies with limited data points. So I didn't specify that before, but when we estimate a dose response model, we actually are requiring that each studies are providing at least the same number of non-referent doses as the number of parameters that we're estimating. So basically those studies presenting only one non-referent relative risk will be excluded from a nonlinear analysis. This is not the case from the one-stage procedure, and here I'm just showing using the additional data in the dosresmeta package how we can add some more data that got excluded in the main analysis, and how to estimate the actually dose response model using in a one-stage procedure just by specifying proc equal to one stage. So here is how the two results change. They don't change a lot, but we see that with the one stage we have even a further reduction in the predicted curve. The second extension that I'm covering is the application of this dose response methodology in the case of drug pharmaceutical studies, where the outcome is not a log relative risk, but is usually expressed in terms of means or difference in means. Have a look at the paper and contact me if you have any questions. And I will conclude with some references and codes. Here on the main web page you can see some reproducible code of the article have been published, some analysis example, and additional useful code for tackling some particular aspects you might be interested in. I've also have a look at my GitHub repository, where I have also the package and some of the presentation and additional material. Some of the slides that I've been presenting and the user in 2016. This is a little bit of update of those, an extension of those slides. And then if you're interested in playing around, I also develop a Shiny app, so you can have a look at that as well. And then some of the articles that I've been covering, the package in the journal Statistical Software, the additional methodology, one-stage methodology, or dose response meta-analysis of differences in mean, and the original article where I published the results on this applied dose response meta-analysis. Feel free to contact me if you have any question or find any bug in the package. I hope this can be helpful for you. Thank you for listening.